Hello and welcome to another sensors tutorial. This time we're looking at the ultrasonic rangefinder. This one is specifically the HC SR04, a very ubiquitous one. There are a few others out there that you might come across, some with 3 pins instead of 4, but they work fundamentally in the same way. And so we're going to take a look at how to do that. To start off with, let's hop into Tinkercad circuits and take a look at how we'll actually hook this up to the Arduino. Then we're going to see what's actually going on when we use this, and then I'll show you the code to make that happen. Essentially what we have here is one speaker and one microphone. Essentially it sends a pulse of ultrasonic sound, a sound wave out through the world. It bounces off something and returns, and the speaker picks up that the microphone picks up the return of that pulse. And based on the time that took, we can know about the distance because we, in general, know about the speed of sound in air. So how do we hook this up? There's 4 pins. They're labeled VCC, trig, echo, and ground. Very straightforward. We're going to take VCC, that means voltage, and hook that up to 5 volts. I'll make this nice and red. We're going to take our ground and hook that up to ground. We'll make that a nice blue. These two, trig and echo, these are pins. One we need to control and the other we need to sense, but they're both digital signals that we're either sending or receiving on these. So we're going to hook them up to 2 of our digital pins. So I will choose pin 2 for trig and pin 3 for echo. I'll make that a different color. You might wonder why I always start on pin 2 instead of starting on pin 0. This is because if we're ever using the serial communication, that way that we send messages back and forth to the computer and the Arduino, that actually uses digital pins 0 and 1. So if we try to do other stuff with those pins, it's going to mess up our serial communication, and our serial communication is going to mess up what we're trying to do with our devices. So if we're using serial, we can't use 0 and 1. So always just best to start at 2. That's as straightforward as it needs to be to hook this thing up to an Arduino. You could do this on a breadboard. It's pretty easy though to just do it on just with some jumper wires from the Arduino straight to the ultrasonic. Just make sure you've got jumper wires that have male on one end and female on the other end to make that connection. What we're going to do next is take a quick look at the oscilloscope, which is a handy tool for seeing digital signals, and see what's actually going on with this ultrasonic rangefinder while it's working before we step into the code. Okay, so this is the screen of my oscilloscope, which is basically a multimeter, but it gives you the graph over time. So we get the voltage changing over time, which is really helpful for us to see what is going on with signals. So what we see here is I've got one probe of the oscilloscope connected to the trigger pin on the ultrasonic sensor. Every so often we're getting this pulse, so this low to high pulse that is lasting, I believe, about 5 or maybe 10 microseconds. We get this pulse, this low to high pulse, this up and down right here, and that's lasting about 5 to 10 microseconds. So it's a very, very quick pulse. But that is the signal that we need the Arduino to send to the ultrasonic to tell it to please make a measurement, send out a pulse of ultrasonic and sense how long it comes back. So I'm going to turn on the second channel here, and this blue signal is from the second probe, and that's connected to the echo pin. And what happens is once the ultrasonic gets this low to high pulse on the trigger pin, it then sends out a blast of ultrasonic, a pulse, and when it does that, it puts its echo pin high. So that's happening right here. The echo pin goes to high. And then that echo pin stays high for as long as it takes for that pulse of ultrasonic to go to an object and bounce back and come back and hit the microphone. And when it does that over here, it brings that pin low. So I'm holding this sensor in my hand, and I'm going to move it now closer to a little box that I have set up in front of it, and you see that pulse shortens. And as I move it away, that pulse widens. So our goal with the Arduino is to measure the time it takes for this pulse to be high. If we know that time, we know how long it took for the sound to reach the object and come back. And because we know the speed of sound, we can use that to figure out how far away that object was. So this was just a really quick look at an oscilloscope. We're going to see a few other examples of where it's handy to be able to look at digital signals like this and see them changing over time. And if you want to take Robotics 30 next year, we'll do a lot more interesting stuff with the oscilloscope and can play around with it if that's something you're interested in. So let's hop over to the Arduino code and see how we can actually accomplish this in code and see what we get back on the serial monitor. So this is the Arduino code that's just running on the Arduino we were looking at in the oscilloscope. I've already written it out. We'll go through line by line, but rather than watching me type, this will just be a little bit faster. Some of these parts will be familiar, but there will be a few new Arduino instructions that we'll take a look at in this. So the first thing we'll see up in setup is 2 calls to pin mode. Specifically, we're setting pin 2 as an output pin. And remember, pin 2 is what I had hooked up to the trig or trigger pin on the ultrasonic. And pin 3 is set up as an input pin. And I have pin 3 connected to the echo pin on the ultrasonic. We're also starting our serial communications with serial.begin 9600, same as we've seen before. That's all we have to do in setup. Just get the hardware ready to go. And then every time through the loop, this is where we're actually getting a reading from the sensor every so often. So the very first thing that I do is I'm setting up 2 variables, one called duration and one called distance. They're just going to store integers, and we'll see what I'm going to use these for in a second, but I'm just getting things set up at the beginning. Now this section here, this is that pulse, that very thin pulse that we saw on the oscilloscope on the trigger pin. So this is how I'm actually causing that to happen in the Arduino. First, I'm writing pin 2 to low, just to make sure that it is actually already low. Then I'm doing this delay microseconds 5. This is just a way to tell the Arduino pause what you're doing for this many microseconds. So I'm saying pause for 5 microseconds, just long enough to make sure that that pin actually did get low if it was high already for whatever reason. And then we're going to say digital write pin 2 high. So we're telling it go up to 5 volts. And now delay microseconds for 40. So 40 microseconds long. And then turn back off, digital write to low. Okay, why specifically 40? It's a little bit arbitrary. I could have this be a smaller value. There is a specific pulse width that the ultrasonic is expecting on this trigger pulse to tell it, hey, I would like you to send out a pulse of ultrasonic. And I believe it's somewhere around 10 microseconds. But I've bumped it up a bit to 40 microseconds to make it a little bit wider, just so we could see it better on that oscilloscope. But if we were doing something where we needed to make sure we were getting readings as quick as possible, we could lower that down. So once we do that, we pulse the trigger pin high and then low. As soon as it senses that falling edge from high to low, the ultrasonic is going to get prepared to send out a ultrasonic pulse and then wait for it to come back. And remember that when it does that, it pulls its own echo pin high. And that echo pin stays high for as long as it takes for that ultrasonic pulse to go to the object and reflect back and gets picked up by the microphone. And then it's pulled low. What we want our Arduino to do is time how long that takes. And we do that with an Arduino function called pulse in. There are other ways of doing this. You could start keeping track of the time when it goes high and then figure out what time it is when it comes back down and then do the subtraction. But this is a built-in way to do it, so it's a lot easier. So pulse in is a function that needs 2 numbers or 2 parameters. The first one it wants to know is what pin is it expecting to see this pulse on? And then is it a high or a low pulse? Everything we saw on the oscilloscope was a high pulse, right? From low, and then it came high, and then back to low. That's what we call a high pulse. There's such thing as a low pulse if a signal is usually on and then dips off and back up. That would be a low pulse. We're expecting a high pulse here on pin 3 because that is the pin connected to the echo pin on the ultrasonic. So this function returns a number, and that number is the number of microseconds it took for the pulse to get there and back, whatever object it hit. We're going to store that number in that duration variable that we set up earlier. Now, knowing that duration is interesting, maybe there's something you want to do with that, but in most cases, we actually want the distance. And you'll all know from your physics classes, speed is just the distance divided by the time. We can rearrange that formula and solve for distance. Now, I'm not going to go through the math here. You can do it on your own and figure out why exactly this number. But it turns out if we want to get the number of centimeters away something is, and we know the number of microseconds it took for sound to get from our thing to that object, we can just divide that time by 29.1. This number comes from some math with the speed of sound. But you'll notice actually the math that I'm doing here is not just dividing by 29.1. The first thing I'm doing is I take the duration and I divide it by 2. And that's because the ultrasonic is measuring the time it took for that pulse to get from the sensor to the object and bounce back. So it's actually making 2 trips there and back. So if we were just to figure out how far sound can travel in that amount of time, we would actually be getting double the distance to our object. So the first thing we do is divide that duration by 2 to get how long it took to just get there. And then we're dividing that whole thing by 29.1, which is this magical constant that converts microseconds, which is 1/1,000,000th of a second, into centimeters. And last but not least, we're just going to print that to the serial monitor, that distance. Now, the last thing I'm doing here is a bit of a delay, and this is usually a good thing to do if you're writing to the serial monitor. It's possible to kind of overwhelm the USB connection between your Arduino and your computer and get some messages a little bit garbled. So if you're sending messages over serial, especially if you're doing it really fast, like you don't have a lot going on in loop, it's usually good to put a small delay. Even 50 milliseconds is enough. And so you'll notice we have delay here and delay microseconds. These are 2 Arduino instructions that do basically the same thing with a minor difference. The units here for delay microseconds is obviously in microseconds, 1/1,000,000th of a second, 1 times 10 to the negative 6. And delay, the default unit is millisecond, so 1,000th of a second. So this is 50 thousandths of a second, which is long enough to kind of give a little bit of space between our serial messages that we're sending so that we don't overload the serial connection. So I have this code running on this Arduino, and I've got it plugged into the computer for serial communication, and I've got the ultrasonic plugged in the way that I showed earlier. And so let's take a look at what kind of messages we get over the serial communication. Okay, we've got a stream of numbers. I'll try to hold this really steady as I point it downwards towards my desk. And so it looks like around 15 or 16 centimeters. And if I look, that looks about right. I could get a ruler out and measure, and I think we would be pretty close. But as you can see, I'm moving this down towards my desk right now, and we're getting smaller and smaller numbers. Now, these work pretty well up to about 4 centimeters. And then as you get below 4 centimeters, things start to get a little funky. You notice some really big numbers there, 60 all of a sudden. So it's getting a little bit confused. Likewise, if I try to measure across my room, I'm pointing it beside me now to the far wall, which is much further than 80 centimeters away. So there is some maximum limit as well. The reason we have these limits is because of the physical properties that we're dealing with here. First of all, that close limit. Why can't we measure closer than 4 centimeters? Remember that we've got 2 separate cylinders on that sensor. One is the transmitter that emits a ultrasonic pulse, basically a speaker, and the other is a microphone. And what we're counting on is that the signal from the speaker can go forward, bounce off something, and come back and hit the microphone. If that object is too close, that sound won't be able to bounce back in such a way that it can actually hit the microphone. It doesn't have enough time to radiate outwards enough. Same thing happens when we try to measure something that's too far away. And that's because over time, that pulse widens and widens, spreads out like a cone. And so by the time it gets back, not a lot of that signal is actually hitting the microphone. So there's that kind of optimal range between 4 centimeters and about 80 centimeters where things are pretty reliable. Now, once you get beyond 80 centimeters, you probably don't need to know distance to the kind of precision that we can get on something like this. So you might use something a little bit more crude or not worry too much about sensing distance, maybe looking for some other things to sense. For the kind of projects that we do in our class, that range is plenty, especially for like little maze runners that need to detect if there's a wall a few centimeters away or not. Now, this example that we're dealing with here is pretty simple, right? We're only getting integer values. We could, in fact, get the decimal values and measure between centimeters, 4.5, 4.7, whatever. It just depends on the application if you need to do that extra work to make sure that you're bringing numbers in and converting them into floating point units instead of integers. For the most part, knowing just the integer value in centimeters is enough granularity for what you need to get done. So this is kind of the bare minimum code that you need to set up the ultrasonic rangefinder. Pretty straightforward, but this is the only one that I would really consider a active sensor in this sequence of sensors that we're studying, because it's something that we actually need to send a signal to for it to generate any signal for us back. All of the other sensors that we're looking at just passively produce a signal just by existing in the world. This is one that we have to say, hey, please take a measurement, it's time, and then we're interpreting what it does after that. So that's it for this video today. We're still going to look at a few more sensors, including rotary encoders, which are very interesting little devices that let us measure with incredible precision rotation, and that can be continuous rotation beyond what a potentiometer can give us. We'll also look at thermistors, how we can measure temperature, which is a very straightforward, very simple one, but we do need to talk a little bit more about breadboarding and circuitry. And then the last one we'll do is measuring sound with a microphone. And then how can we amplify that signal, because the little microphones that we have in the lab don't generate a very large signal, and in fact pretty small, almost too small for the Arduino to detect any changes. So still those 3 more to come. I hope you're following along and inputting all of this information that I'm spewing out into your own document, not only for your own reference, but to submit as evidence that you know this stuff so that I can give you the credits. Okay, take it easy. Have a good one. Bye.